Thank you very much, Gustavo, for that very nice introduction. Definitely really happy to be here sharing to folks that seem to be all over America and potentially worldwide. So yeah, I'm gonna go ahead and share my screen here and hopefully folks see it. And yeah, gonna get started. Let me open the chat just in case. Okay, so hi everybody. My name is Darren. It's really nice to meet all of you. And today I'm going to be talking about the investigation of tremor and explosion sequences from Pavlof Volcano, Alaska, using deep learning. And just a quick shout out to all my co-authors here who have contributed to this project. So as a quick overview of today's talk, I'm going to try to keep it relatively simple, but also kind of covering the details of machine learning. I'm going to start off with the motivation of why we use machine learning for Pavlov Volcano. I'm going to talk about the model that I'm using, the data that I'm hoping the model classifies, and also how we kind of label data and train the model itself. I'm going to talk about ML results, of course, and kind of discuss pros and cons, because I feel like nowadays it's like the Wild West of machine learning. It's very easy to be overly optimistic about machine learning, but trying to keep things real. And if we have time, we can talk about recent explosion location work that I've done that goes beyond machine learning, but we'll see if we have time. So if you happen to be at my talk at AGU last year or SSA this year, there will be some overlap, but I hope to cover some additional nuances here with the additional time that I have. But otherwise, even if you were at those talks, I can guarantee you that there'll be the later parts will be certified fresh. So there's something for everybody. So to start off, let's talk about tremor. So what is tremor? So volcanic tremor, from the geophysics perspective, is a seconds to minutes long, semi-continuous seismic or acoustic signal that's usually seen around volcanic eruptions. It's notoriously hard to detect and classify, mainly because of its highly variable amplitudes. It tends to be emergent rather than impulsive like an earthquake. It's also really long in duration, and it has widely varying spectral features. At volcano observatories, for example, the Alaska Volcano Observatory that I work with, we often monitor tremor exclusively on spectrogram images. And I've kind of attached a figure here at the bottom of the slide showing what a spectrogram is. So at the very bottom, it's a waveform. And then at the top, you can see the spectrogram from the seismic data at Pavlov Volcano. So if you look at it, for those who are unfamiliar with spectrograms, you might think of it as a visual way to look at waveforms. And if you think of sound waves and a human speech, it might manifest itself as a spectrogram at different frequencies as it resonates within our mouths. Or you might think of a kettle whistle, which might manifest as a sharp peak on a spectrogram. But here I'm looking at seismic data, not sound data. So you might think of ground motion being concentrated at a really particular frequency over time. And it is these sharp peaks over time that we're trying to detect and classify at the volcano. So if you look at spectrograms, they're essentially images. So it really presents itself as a machine learning opportunity. You might go on Google, you want to search something, and you might, get a CAPTCHA, and you're supposed to click parts of the picture that are a car or an airplane. So here, instead of classifying cars, airplanes, cats, or dogs, we're really classifying signal against noise. So at the Alaska Volcano Observatory, we really want to automate this process of classifying spectrograms because it's hard work kind of monitoring more than 30 volcanoes on a daily basis. And in Alaska, we have lots of local seismic networks at each volcano, and we have a duty seismologist that go in like twice a day to look at these spectrograms hour by hour, station by station, across the different volcanoes. So wouldn't it be nice here to kind of just have a tool to tell you, or at least focus your eyes on places where we think there's some anomalous things going on. So here I've kind of like screen captured two examples, one from Pavlov, one from Semisopochnoi, from when they were experiencing unrest. So hopefully we will be able to automate this. So with that, I would like to introduce our machine learning model. We call it VoiceNet, which stands for Volcano Infrasound and Seismic Spectrogram Neural Network. And we have the logo here at the bottom left for branding. At its core, VoiceNet is a convolutional neural network that is typically used for image recognition from machine learning world. The seismic world is not a stranger to this. It's been used on seismic waveforms to detect P and S arrivals. And here we're really just transferring that to apply it on spectrograms. And what's novel here is that we're kind of applying the convolutional neural network, VoiceNet, on a moving spectrogram window, kind of classifying as we go along in time. And for formality, I've kind of added the architecture here, but we could revisit this if we want to talk about it. So with the architecture out of the way, let's talk about the eruption. So Pavlof volcano, which is the volcano I'm studying, previously erupted from August 2021 to December 2022. It's a pretty long eruption, a year and a half. It's also really frequently erupting, having last erupted in 2016, 2014, 13, and back in 2007 as well. So for the 2021 eruption, it's kind of characterized by intermittent low-level explosions and lava effusion. You might see the GIF here at the top, kind of showing these little puffs coming out of Pavlov volcano, which from a volcano standpoint is kind of pathetic, but it's long-lived and low level, and it gives us a lot of signals to work with. And this, coupled with the pretty well-maintained network of the time over that 1.5-year-long eruption, really presents itself as a really good opportunity to explore the feasibility of ML tools and kind of characterizing the eruption in both tremors and explosions. So CNNs, or convolutional neural networks, are essentially a supervised machine learning model, so it needs labeled data. But before I come up with labeled data, we want to select a number of classes. So what we did is that we manually browsed through about 5 months of data to decide what classes we want. So I have here on this panel the classes that we selected for seismic data. So we have 3 different tremor types: broadband, harmonic, and monochromatic. And you can see down to 5 stations how they look like, from like 0.5 hertz to 10 hertz. So broadband kind of spanning a wide range of frequencies, harmonics having a few sharp spectral peaks, monochromatic having just one dominant spectral peak. And we also want to look at impulsives like earthquakes and explosions, which are transients, and also noise, because we want to detect a signal from noise. We also want to look at infrasound, and infrasound is a lot noisier, but here we decided to collapse all tremor classes to just one infrasonic tremor, kind of manifesting itself as a peak around 2 or 3 hertz. Explosions, again, show up pretty nicely on infrasound. And then there's a lot of wind noise and occasionally electronic noise. At the very bottom, I've kind of shown, after labeling, how much of each class that we got. And this was primarily done through this open source software called Label Studio. Definitely recommend it. And what we do here is that we produce these spectrograms and we kind of draw boxes around where we see each class type. And after that, we will cut up each box, and then it would be our labeled data. So as with most volcanoes, we don't usually see the uniform representation across all signal types. There's definitely some disparity and class imbalance. So here I'm showing the bar graphs of each of the different class distributions in seismic and in infrasound. So bear in mind, this is a linear scale, then goes to a logarithmic scale afterwards. And we want to do some class balancing so that we could train a reliable model. So how we did this is that we used the surplus of noise shown by how high the noise bar is to augment our data. So in cutting up the 4-minute spectrograms, we basically take one of the harmonic tremor classes, for example, and we add in 35% noise, kind of like stack those images together to get this augmented new harmonic tremor sample. And we do that for the classes that are sparse to kind of taper off at a pretty reliable number without overdoing it. So this dashed line is where we establish our balanced number, and we use that balanced data set for our model training. As with most machine learning efforts, we want to look at the learning curves, and the smoother they are, the better. And eventually, we want to capture when the model is the lowest at its validation loss. So when it's getting the least things wrong. And ultimately, we don't want to overtrain it. It's usually shown by a divergence of this validation line, and we want to capture that minima where our model does best on our validation set. So after that, we apply our model on our test sets, and this is a confusion matrix. And how it works is that in every little cell, it shows the ratio of the class that it gets right, the left axis being a true label and the x-axis being the predicted label. So down the diagonal are the ones that it gets correct. So overall, our seismic model does pretty well. It's like 81% accuracy. And our infrasound model does achieves 90% accuracy, but although across less classes. So, and down the diagonal, we can see in general, it gets things right pretty often, which is good. But of course, it's not all glitz and glamour already. We want to scrutinize this matrix to see what it's getting wrong so that we know how to improve. And you'll notice that across the different tremor types, there's some confusion. This is perhaps expected because tremor tends to blend from one type to the other. And also against earthquakes and explosions, this is a really hard problem. There are dedicated models to achieve this. And you can see that our accuracies are not the highest here, but we still find value in the model. On the infrasound side, we see the primary confusion is between explosions and wind. This is also perhaps expected because explosions, sometimes we don't get them when they're obscured by wind itself, or if SNR is low. So that's our confusion matrix. One additional check that we did is to permutate randomization seeds. For those who are familiar, you might hear of K-fold cross-validation. This is a different way to achieve the same thing, where we permutate a random seed before we do our data set splitting. So with our labeled data set, there's of course train validation tests. And when we cut it up, we might just get a lucky draw or a particularly unlucky draw of what we get. So this is a way of doing this whole data splitting process 50 different times for each model, so that when we compute and compile the test accuracies, we can see a histogram just to make sure that our selected model in red does not differ too far from the mean performance, because we don't want to get like a particularly fortunate or biased draw when we do training. So one last validation piece is GradCam. So GradCam stands for Gradient-Based Class Activation Mapping, and it's a way of highlighting what the convolutional neural network looks at before it gives its classification. And it's kind of mapped out in opacity here for a few select examples that I'm showing over here. So you might notice for harmonic tremor, it's looking right at the signal, and that's a good sign. I think machine learning has a reputation for being a black box, and methods like these are in a way to take us a step towards interpretation and making sure that we're doing things right. So yeah, with all these pieces in place, we kind of found confidence with our model. We're happy with it, and we decided to apply it and let it loose on 2 years of seismic and infrasound data bounding the eruption. But of course, before I jump ahead and bombard everybody with a 2-year timeline, I'm going to look at some finer timescales to better understand how this machine learning model works. So here's a typical timeline figure that I showed in my recently published paper. And I know it's very busy, so let's step through it together. So at the bottom 5 panels, we have the spectrograms from the 5 stations around Pavlof volcano. Every 4-minute window with some overlap is being classified and kind of placed at the top here, with the corresponding color bar of each class on the right side. So you see here, we get the monochromatic tremor. It's classifying it blue, so it's getting it correct. Of course, we apply our model on single stations, and there are times where stations to stations, the classifications don't agree. So in those instances, we sum the probability of the different classes across all stations to get a network vote. And that's indicated by this voting row here, showing a network-informed result. Correspondingly, we have a probability for this network vote, which we present here as a time series. So you can see here dipping when there's disagreement or if there's a data gap. And yeah, so in one more panel, we plot reduced displacement. This is somewhat similar to RSAM, just get a sense of amplitudes. Just bear in mind that our model looks solely at spectral images. It doesn't really have as much amplitude information, which is why we want to present it alongside to see that, hey, it's brown here, and we have a high amplitude. It's a real explosion. So in a nutshell, our model within this 3-hour sequence during the eruption does accurately identify this progression from the blues, the monochromatic tremor, the grays, which are noise, and then some transients, and then broadband tremor. So it does pretty well. And we really like the network vote because it kind of suppresses erroneous class returns, and it gives us a higher confidence thing to work with, which is important if we want to do eruption forecasting or monitor volcanoes. So on the other hand, I'm showing a similar figure, but for infrasound and spanning 3 hours as well. Classifying infrasound does get really messy because it's really noisy. You could just see from the spectrogram, there's a whole lot of incoherent stuff going on, almost like a bear is just blowing into the microphone in Alaska, right? And yeah, but overall, we do see that our model flags up the 3 explosions. You might see these little lines in the center as this beige color for explosion. And likewise, for infrasound tremor, you might see on the 3rd station down and the 5th station down, it's lighting up in purple where it should light up purple. So that's a good sign that it's working. although the network vote, due to the incoherence, faces some challenges. So probability across the board is pretty low. Okay, so with that, now I'm going to bombard everybody with a 2-year timeline. So here's the application to Pavlov from January 2021 to March 2023. At the top, we have the AVO color code. It's a proxy for volcanic activity. And you can see here we are color code green, yellow is unrest, and an active eruption in orange. One panel down, we're looking at the seismic spectrogram, but it's really squished here since it's 2 years of data. And then in the third panel, the seismic classifications. So you could see here I've kind of used acronyms for each class, but broadband tremor pretty much dominates the entire eruption. And you can almost see it here in the seismic spectrogram too. We notice more tremor diversity, different tremor types during the unrest phase, perhaps even before when AVO went to yellow, which is a good sign. And then we see quite a lot of earthquakes and explosion classes. But what's perhaps really interesting is to see this kind of nested explosion periods here in the middle of the broadband tremor, showing that there's some explosive periods kind of buried within there that could have been missed. We do the same for infrasound. The spectrogram's really ugly, but we do see here in the infrasound class distribution that we get more infrasonic tremor near the unrest phase and near the tail end of the eruption. Now, those of you with a keen eye might have noticed that we do see some explosions before the eruption even happened. And this is actually a misclassification. There were some long period earthquakes during the time that were misclassified. And I'll talk a little bit more about that later. So at this very bottom, we're plotting a high resolution or high confidence explosion timeline. And how we do this, it was kind of a mitigation method after seeing these bad explosions in both data types here from the machine learning effort. We wanted to combine both seismic and infrasound information. So how we kind of derive this high confidence timeline is that we looked at windows where the seismic model and infrasound model gave the explosion class at the same time. And for those instances with a greater probability than 0.6, we kind of draw this black line here. And it seems to align pretty well with this independently determined RTM infrasound explosion timeline. So a good check that data fusion helps. So this is a lot of information. It's 2 years worth of information, but we wanted to look at some periods to kind of verify these with webcam images. So here, I've kind of identified periods where we have explosion-rich activity, and we want to compare that with some webcam images. We also want to look at periods with no explosions, but we see lots of voluminous steaming. And likewise, I want to look at why were there so many misclassifications from the explosions from both data types during the early phases of this time period. So starting from December 4th, this is an explosive period. Here I'm showing 6 hours of data and the classifications above. Overall, we see several periods where it goes brown, and here we can see a corresponding explosion in the spectrograms, so it's a good sign. But when we look at the webcam images at Pavlof Volcano, bear in mind this is Alaska, so 30 minutes in between each image, we do see pretty nicely at panels E and F a pretty convincing ash plume, which shows that yes, it's indeed exploding, and that we can trust our machine learning model to identify explosive periods buried within. However, when we look at the other time period with no explosions and just straight broadband tremor, sure, it looks uneventful. It looks like nothing much is going on, although the model gets it right. But in fact, if we look at the webcam images, it's voluminous steaming. There's active lava effusion from satellite images, which goes to show, although I'm a seismologist, that seismology cannot answer it all. We need remote sensing methods. We need multidisciplinary efforts. And I could guarantee you that this lava effusion was probably captured on thermal data. So everybody has to work together. And lastly, let's look at one of the earlier periods with long period activity. And this is when you could see just from the top how much confusion there is. It's getting it wrong, calling it explosions, when in fact they are long period earthquakes at a time where the volcano is not erupting. So we think this is definitely an oversight. On hindsight, we definitely should have included a long period class, a dedicated one, but we unfortunately did not see it during the time period where we scanned our data. So spectrally, I kind of agree that the long period earthquakes look most similar to the explosion. So I don't fault the model here, but there's just more work to be done here to improve our model before we could let it loose on operation at a volcano observatory. So, nevertheless, we do think that the characterization of the 2021 to 2022 eruption was pretty cool. And since we had the data and we had the model, why not just try it on the prior eruptions? So as I mentioned, Pavlov volcano is frequently erupting. It last erupted numerous times, 5 times between 2007 and 2016. So here we kind of do the same thing and just look at the seismic summary. We kind of set aside the infrasound model due to the lack of infrasound data for earlier eruptions. So here I'm showing the prior eruptions, 2007, 2013, 2014, 2016, relative to the explosion onset as determined by the AVO color code. So for every set, you see the AVO color code at the top, and then the seismic classes, one panel under it. Every little pixel here is 1 day, and here I'm showing days since eruption onset. So lots of things going on here, but when we align these different eruptions through time, what we see is that most eruptions began with or were closely followed by the rapid onset of broadband tremor, which goes to show that broadband tremor is likely a good indicator of eruptive activity at our volcano. Unlike the 2021 to 2022 eruption, past eruptions don't really show any precursory unrest. The 2021 eruption was preceded by weeks to almost months of different tremor diversities, whereas for the past 4 eruptions here, we don't really see too much evidence of that. We also see that broadband tremor and the eruption itself exhibits a broad range of timescales. It was a year and a half, or I guess broadband tremor was over a year for the 2021 eruption, 4 weeks for 2007, but only a few days for 2016, which goes to show the eruption diversity that Pavlov has. But what perhaps is the most interesting for us, at least, is that the 2007 eruption, which lasted 4 weeks or so, came from the southeast flank crater, and so did the 2021 eruption that lasted 1.5 years. In contrast, the 2013, 14, and 16 eruptions are short-lived, and they had vents in the summit crater. So we suspect there are 2 different vent systems, might have different longevity in terms of their eruptions and different unrest signals. We do see a lot more tremor diversity here for the summit vent eruptions, lots of greens and blues, and also kind of resurgent activity by turning off the tremor, some period of quiescence, and then kicking back in. So overall, this kind of poses a few open research questions that I'm currently still working on. Number 1 is, does Pavlov show event-specific unrest? Here it seems pretty convincing in seismic data, but I want to look at other data forms from the multidisciplinary perspective to see if that's indeed true. And a later question is, how open is Pavlov's conduit? Pavlov is often seen as an open system volcano, but if it shows different unrest signatures from vent to vent, can we actually call it open? And what does that mean from monitoring and eruption forecasting perspectives? So open questions. So in the previous slide, I kind of showed a summary of all these different eruptions, but if we really zoom in, I just wanted to share that VoiceNet can also be run in near real time. And if you run it in near real time, we can go down to the minute to see when tremor itself started. And in a way, it's a good way if we can run in the background to detect eruptions as they occur, wake someone up. Okay, so VoiceNet, a future utility for AVO and hopefully elsewhere. So let's discuss some pros and cons. So I think one of the key selling points of VoiceNet here is that it augments a seismic analyst role. Right at the start of this presentation, I kind of showed how much spectrograms a duty seismologist has to look at. And here, if we can provide a summary timeline, kind of condensing all this information to maybe one quick figure, it's a good way of kind of tracking different volcanic activity over a long duration of time. And we've kind of showed it here for Pavlov volcano that a 1.5-year-long eruption can be summarized just on one little panel there. We also note that station-independent application is useful because it could, when the eruption happens, you can have stations going in and out, you can have station problems. So your number of stations can change. But when we do it here independently by station, we add on a network vote, and we think that's really useful in kind of having a network-informed result, but also flexibility as these stations go in and out. We also demonstrate for Pavlov that it generalizes well for prior eruptions. So a natural next step is to see whether it could work well on other volcanoes. And we're currently in the midst of testing that. And the cons. So VoiceNet, it kind of requires an exhaustive set of classes. So recall how we did it. We look at individual spectrogram windows, 4 minutes each, and we kind of force the model to return one class every time step. It could be noise, 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 tremor. But one problem is that when classes are superimposed, it's kind of forced to choose one. So you might have an earthquake kind of overlying tremor, and then the model here would kind of struggle, but generally our convention here is to prioritize the transient signal. So, and one last con here is that VoiceNet does not give a precise origin time for transient signals. You might think of volcanic earthquake catalogs. Those require an onset time of the P and S arrivals. But here, because we're classifying the whole 4-minute window, we can tell you that there's an earthquake or explosion within the window, but we cannot tell you at what second did your explosion happen or did your earthquake happen. So that's future work. I'm currently looking at diving into a higher resolution explosion catalog to kind of look at the explosion locations and whatnot, which we did not have when applying this ML model. So future work, my advisor, David Fee, and others are currently working to enhance VoiceNet. Like I mentioned, we really want to add an additional LP class to try to make it less confused of explosions. And we want to incorporate data from a whole bunch of different volcanoes using data from worldwide. We have international collaborators, and we're hoping to build this generalized seismic model. For myself, for the rest of my PhD, I'm looking at event-specific unrest. Like I mentioned, I want to look at multidisciplinary data and from Pavlof volcano. And I want to look at explosions that precede or predate the local infrasound network. I'm looking at ground couple airwaves. I know it's a loaded term, but they're essentially explosions that then couple into the ground and are getting picked up by our seismometers. And hopefully I'm trying to locate these explosion sources to kind of map out when was the southeast vent active and when was the north vent active. And as a closing statement, so my VoiceNet paper has been published. It's on JGR, link is over here. And my repository with this model is also public. So if you'd like to try it on your volcano, please feel free. Although I would say, since it's trained on Pavlov, I would not expect it to do perfectly well on a different volcano yet. So take it with a pinch of salt. And with that, I can stop here. And I'm happy to take questions or discuss.
Very nice, Darren. Yeah, let's see if we have any question. If you want to ask a question, please unmute yourself, or you can also type it on the chat box. Well, I can ask a question.
Sure.
So, when you mentioned the explosions that were not seen in the seismic data, and like talk about thermal data from satellite, I wonder if like you are already thinking or like maybe coupling your satellite data to these kind of models, since like wouldn't it be kind of like an easy task if it's all like signal analysis at the end of the day, or image analysis at the end of the day?
Right, right. Yeah, that's a good question. I wonder if I have a bunch of extra figures here. Yeah. Okay, so this is kind of like the full figure that I had from my paper. So there is another grad student who has since graduated from UAF that actually looked at CNNs on kind of satellite-based hotspot images. And these little black dots that you see on this panel are places where he has found thermal anomalies. So we did try to align these, but I don't think we see anything that's overly systematic, maybe some higher radiative power values at some explosion depleted periods, which might indicate lava effusion. But these are kind of broad strokes comparisons, but we haven't really found any fine-grained similarities in this multidisciplinary data yet. Although, that said, one thing that I was pretty curious, here we're showing ML-based determined radiative powers, but I was curious based on the resolution of the satellite, whether or not we could see if the location of the hotspot overlays the southeast vent or the north vent. but I kind of have to poke my collaborator here, and then we'll see where it gets to after that.
Yeah, thank you. We have
Mhm.
a question in the chat from Alex. Um, so it's Alex's understanding that an open system volcano has to do with geochemical petrologic processes like magma mixing. What does open mean from a seismological perspective?
Sure. Yeah, I'm happy to answer that. So I think open from a seismological perspective, in a nutshell, I would say hard to forecast. But I I think the best way I could explain it is that for a closed system volcano, you might imagine, a dome or a cap in the magmatic system kind of obstructing the conduit so that when the volcano reactivates, you kind of expect as magma ascends, that rocks to break for the system to be pressurized and for earthquakes to be generated. For at Pavlov, because we don't see very many seismic precursors at all, we suspect that the conduit's open and therefore magma could ascend pretty much unobstructed. And perhaps due to the brittle ductile transition there, we don't see a lot of earthquakes. You don't really see very many seismic signals in the lead up to an eruption itself, which is why monitoring Pavlov itself is so challenging because we tend to see tremor right as it starts, but really nothing beforehand, which kind of motivates us kind of scouring the data with machine learning to see if we find anything else that we might have missed.
Awesome. So, question from Alicia. Have
Mhm.
you thought about what you might attack next after trying to generalize the model? Another different machine learning approach, maybe? Continue to try to generalize? Where do you want to go with these kind of tools?
That's a good question. Let's see. So I think the first part about generalizing the model, uh, well, first of all, I want to fix this explosion misclassification, which is why we really wanted to add LPs. And I think there's been a lot of enthusiasm about a volcano as we've kind of showed its success at Pavlov to kind of generalize it to different volcanoes. And I may have, um, I wonder if I have, yeah, here is one. Okay, early feature of the generalized model. This is still in progress, but this is an application to semi-Sapachnoi, kind of showing where it gets these different tremor types right. But so yeah, so first of all, we want a model to do better, and hopefully we could apply on different volcanoes just to um, see how far we can take this model. But for me, as a person from a personal standpoint, I feel like as a volcanologist, I think machine learning is cool and I like to apply it. But at the same time, we've done all these classifications. A big question for me is so what, right? So the idea here is to get these classifications, tie it into multidisciplinary data, and then kind of say something about the volcano itself rather than just giving you a catalog of different tremor types. So that's my personal motivation, kind of leaning back towards volcanology and interpreting process. I don't see myself kind of going too hard on the machine learning trajectory, but it's kind of good to have this knowledge in mind. But if an opportunity does presents itself as a uh, feasible machine learning venture, I'm happy to take a stab at it. But for now, yeah, process, process, process.
We have a question from Joanna. You mentioned additional volcanoes for future work. Are you
Mhm.
thinking global volcanoes or additional Alaskan volcanoes? If so, which ones are you considering as of now?
That's a great question. So yeah, I guess I kind of showed this slide already. So I think since we have many collaborators at Alaska Volcano Observatory, applying it to different Alaska volcanoes makes sense because there's more homogeneity and how far the stations are from the volcano, the type of instruments we use, and kind of we're just used to playing with Alaska data, right? But that said, we have looked at some Etna data as well, and trying to think of where else um, we've kind of labeled data. There's one more place. We added data from Popo volcano, Popocatépetl, and we've kind of tried different test cases from Kilauea, Mauna Loa. So, and right now, I think a paper outline's written, and hopefully it'll be written and submitted somewhat soonish. But yeah, it's exciting that it's worked. But at the same time, we want to highlight nuances and places where it falls short too. It's good to be real with machine learning. Uh, okay, I lost the chat here.
Yeah, that was the last question. If anyone has any other questions, this is your last chance. And while we wait for other questions, I'm gonna share my screen briefly, just give you an update about our next webinar. Oh, also, actually, if you have a friend or if you have students who will be interested on attending this webinar series, you can take a photo of this QR code and share it with them. We also post on the Volcano listserv, so yeah, keep an eye out for that too. And our next webinar speaker is going to be Amiel Nieto Torres. He's a postdoctoral researcher at the Millennium Institute on Volcanic Risk Research, Secular Volcanes in Chile. So yeah, please join us on October 1st, again, to hear more about Amiel's work. Let's see if we have any other questions. All right. Well, I think this is it. Thank you so much, Darren. That was an awesome presentation. Very interesting work.
All right. Yeah. Thank you, everybody. And yeah, thanks for organizing. And I definitely hope to be more active with CONVerse initiatives. This is great.
Yeah,
So,
we're still developing yeah, a lot of initiative for still in like the planning kind of phase. So, but yeah, the webinar series is part of the one of, or at least help us with our goals of providing a platform for grad students and early career researchers. So yeah, join us. As I said, join us in 2 weeks, October 1st. That's going to be our next session. Thank you, everyone, for joining. Thank you, Darren, for presenting. See you soon.
thanks all. Bye.